So in this next section, we're going to talk about autosomal versus X-linked, and we're going to focus on X-linked traits. Remember that autosomal disorders in general are going to tend to affect males and females equally. However, X-linked disorders are going to be primarily males, and the reason for this is because they only have one X chromosome. Remember, males are going to be XY and females are going to be XX. If something is X-linked recessive trait, it is going to be expressed phenotypically in all males because they only have one copy of the X chromosome. It is only going to be expressed in females that are homozygous for the mutation. So the males really, it doesn't matter if they get one bad copy because they only have one X chromosome, so there's nothing to compensate for it. Females, on the other hand, if they get a bad copy, they still have that backup X chromosome and they should be fine. It's only when they get two bad copies that they're going to have that particular trait. So an example of this would be hemophilia. Another would be color blindness. Hemophiliac, let's say a hemophiliac has children with a normal female, and that would be the setup that you would have here. So you have a hemophiliac, I put as a lowercase h, the Y chromosome is unaffected. If they had children with a normal female, she's going to have two normal copies of that gene. And so if you were to fill in the Punnett square, what you would see is that because the males or the sons are all going to get their Y chromosome from dad, all of their sons completely normal, completely fine. However, if you were to look at their daughters, okay, because they're getting this X chromosome from their father, and this happens to be carrying that hemophilia gene, but both of them are getting their normal copy from their mothers. 100% of their daughters are going to be carriers for this particular trait. Again, the daughters are getting their normal X from their mom, so they're phenotypically going to be normal, but they're going to be carriers for hemophilia because they got that copy from their hemophiliac dad. Okay, so let's say that one of these daughters goes on to have children, and we know that now that she's a carrier for this particular disorder. Let's say she has children with a man who is phenotypically and genetically going to be normal. Let's look at the offspring here. So out of their daughters, the daughters have a 50% chance of being a carrier for this disorder and a 50% chance of being phenotypically normal and genetically normal, not a carrier for this trait. Their sons, on the other hand, because they're getting their X chromosome from their mother, they have a 50-50 chance of getting one of these quote-unquote bad chromosomes from their mother. So they have a 50% chance of having hemophilia if they have a son, 50% chance of having a son who's completely normal. And so what you can see though is if a woman is a carrier for this trait, if she has only daughters, and if those daughters have only daughters, or if they happen to get lucky and they only have sons who are not having this trait, it can be undetected for several generations before it might be expressed in a male descendant. And what you can see here is a family tree, a pedigree pattern demonstrating an X-linked disorder such as hemophilia. You can see the original grandparent, this father, he had the disorder. He had daughters, they're going to be obligate carriers, remember, because they're getting that X chromosome from their father. The sons are all going to be normal. If the daughters go on to have children, because that woman is going to be a carrier, she has a 50% chance of having a daughter that's a carrier, 50% chance of having a daughter who's normal. She has a 50% chance of having a son with a disorder, and a 50% chance of having a son who's normal. And in fact, that ratio plays out exactly right with this particular family. And what you can see here, the son did not have any children. This daughter did have a child. She had a male, and unfortunately, she had a 50-50 chance of having a male with a disorder, and unfortunately, they had one with a disorder. If something is an X-linked dominant trait, it is going to affect basically males and females pretty equally, because the males, again, they're getting one copy of it, they're getting a copy, it's going to be the dominant, they're going to have that particular trait. In females, again, they're getting two X chromosomes, and if one of them is the dominant for whatever trait, they will also phenotypically show this particular trait. So if you're an affected male, you have a normal mate, You will have no affected sons because remember your son is getting the Y chromosome, and they will have no normal daughters because their daughters are all getting that dominant X-linked trait. The male and female offspring of the female carriers have a 50% risk of inheriting the phenotype. And so if you're looking at a pedigree, it can be very difficult to distinguish between the pattern between this and between an autosomal dominant inheritance. Really the main key is here, you have to look at the affected males with normal mates, have no affected sons and no normal daughters. Other than that though, it can be very difficult, like I said, to distinguish between the autosomal dominant. Here's a sample tree of this. You can see here is a male. His daughters all have that disorder. A female has a 50-50 chance here, and so on. There's a male, has two daughters. They're both obligate of this. And the males, because they're getting the Y chromosome from the dad, they're all going to be unaffected. If something is a sex-limited inheritance, this happens in cases where the expression of a specific phenotype is absolutely limited to one sex. If something is a sex-influenced inheritance, the sex of the individual influences the expression of a phenotype, but it may not be limited to one sex or the other. And so we'll go through several examples of this because it happens quite often. We use the term sexual dimorphism to describe things that are going to be different in between the sexes. So in many different types of birds, their feathering pattern is going to be quite different between the males and the females. So if you're looking at feather plumage in these chickens, it's actually caused by an autosomal gene, not an X-linked gene. The hen feathering is controlled by a dominant allele that happens to be expressed in both sexes. The cock feathering is controlled by a recessive allele that's only expressed in males. But in reality, and this happens with many of these types of traits, the actual expression is modified by the expression level of the individual's sex hormones. So in females, any of these different genotypes, you're going to get the hen feathers. In males, if you have the homozygous recessive, you're going to have the typical cock feathers. Otherwise, you're going to have the hen feathers. And hormones such as testosterone and estrogen can play a role in expression of these. Another one would be sex-influenced inheritance in humans would be pattern baldness, and sometimes they'll call it male pattern baldness because it happens so predominantly in males. And what we're talking about here is where hair is very thin or absent on the top of the head. It's caused, again, by an autosomal gene. So you may hear these old wives' tales about how, oh, you have to look at the mother, the grandpa, you know, how is this going to be inherited? Well, all we can say is that it's an autosomal gene, and it acts differently in the sexes. So in males, the dominant B here behaves as dominant, but in females it happens to be recessive. So if we look at the genotype, if you're homozygous, capital B here, females will be bald, males will be bald. If you're heterozygous for this, females, because for some reason it acts as recessive in females, females will not be bald, but males will be bald. If you are lowercase b, in this case, the females not bald, males not bald. So I do want to point out females can display this pattern baldness, but the phenotype just overall is going to be much more prevalent in males. When females do inherit this particular phenotype or genotype, the phenotype's pretty much always going to be less pronounced in males than it is in males, and it's usually expressed later in life. It also appears to be very related to levels of sex hormones. So if the levels of, say, testosterone, androgen are maybe a little bit high in this particular female, the expression of this is going to become even more apparent. And there have been cases where an individual may have a tumor, and this changes the levels of the sex hormones, and it may increase the levels of the baldness. So here's an example practice problem.